PSI.
equation.
So project close. Yeah.
I did like, I don't know how many durations. I did like 5.
There we go. So now, project new. So
Can I just see your
leave it at
mathematical equation to see
A. Equilibrium
how it
1.
relates to pressure? Because mine doesn't have any
Okay.
pressure in it.
So we drag the balance, or we double click on the balance, update project, reprocessing, double click, select the working directory,
Select the working directory.
hello? It's thinking, okay. So my samples, is this my samples? Equilibrium, gas, select. That's our working directory. Chemistry set,
Chemistry select.
it's equilibrium gas, select. So now we can edit the chemistry set, and we want to find GRI net, right? So we browse under system data, GRI net. There it is.
Oh, she don't do that.
Oh yeah,
And
we
thermodynamics file, GRI net thermal. Okay? So we save this. Now we can run the preprocessor, and under view results summary, reprocessing has been successful. Okay. Now we double click on equilibrium, and we look at the C1 equilibrium, and we select constant temperature and pressure if we want to calculate the equilibrium constant. So we select 2000 Kelvin. Is that 2000? We select 1 atmosphere of pressure, and we go to reactant species.
Matt, are you recording? You take pictures.
In this case, we need to select the equivalence ratio. So equivalence ratio is 1. And then we select the fuel, let's say CO. There's CO is the fuel, 1 mole of CO. And then we select the oxidizer, auto-populate. You see it's nitrogen 79, oxygen 21. Complete combustion products, auto-populate, nitrogen and CO2. There's no water, of course. So we are done. We go to run calculations. We display detail. We create the input file. Give it a name. And then view the input file. So you see that it's constant temperature and pressure. Temperature is 2000, pressure is 1 atmosphere, equivalence ratio is 1, and we are analyzing CO as the fuel. So this looks good, and now we run the model. Come on, what's going on? This should take a second. Or less. What is going on here?
I think that's very
Oh.
slow.
So we ignore the next step. We're going to look at the next step when we want to construct graphs based on the post-processing software in Kepler. For now, we're going to ignore that and just view the results. Output file. And so here's the output file. So if you scroll down, the numbers that are interesting are of course these. So CO2 is 0.338, right? CO is 0.768, right? And then the oxygen is 0.33 to the power of 0.5, right? So based on the oxygen equilibrium state, CO equilibrium and CO2, we calculate the equilibrium constant, right? Yes?
Okay, so do you see the oxygen is associated into small pieces at
Right.
equilibrium? Would
Right.
we add it to
You
the,
just ignore that.
ignore it?
You just ignore that. right? So it just does oxygen, CO, and CO2, right? And now you do this at a bunch of temperature. So you go back, so you write down these three numbers in a spreadsheet, and then you just go back to C1 equilibrium and say, well, how about if the temperature is 2500? Is that 25,000? Is that okay now? So now you go back to run calculations, create input file, and run model, right? There it is, view results, output file. You scroll down and you write down these three numbers, and you determine the equilibrium constant as a function of temperature, right? The equilibrium constant is not a function of pressure, right? For an ideal gas, as we learned in thermo, it's a function only of temperature. So this is the calculation for CO equilibrium constant. You have a bunch of other problems on the homework, right? That what other reaction are we interested in determining the equilibrium constant? What does the statement of the homework problem say?
No, and NO2
CO?
CO plus 1/2 O2.
Right, but what other reaction? Is it methanol?
N2
plus O2.
Methanol. So now let's try methanol here. So the only thing that you need to change when you analyze methanol, you go back to C1 equilibrium, you analyze reactant species, right? So now you delete you delete CO and you just select the methanol, right? Methanol is CH4O, right? CH4
CH3OH.
CH3OH. This one?
Right there.
This one?
Yeah.
CH3OH. So 1 mole of CH3OH, right? There it is. So now the oxidizer mixture is going to be different, right? Or the combustion products. So auto-populate, it's still nitrogen and oxygen, right? But the complete combustion products, water now is going to appear, right? So we have CO2, water, and nitrogen is the complete combustion product. So that's the only difference. So now we go to run calculations, create input file, view input file, bring it here so that everybody can see it. And so you see that we now have the fuel is methanol, the oxidizer is air, right? And the complete combustion products are CO2, water, and nitrogen, 2500, 1 atmosphere of pressure, right? So we close this, run model, there it is, view results, output file. So now the important thing is to show whether methanol appears in equilibrium, right? So here you say that the equilibrium constant is the CO2, concentration of CO2 times the concentration of water vapor squared, right? Divided by the concentration of methanol and the concentration of oxygen, however many moles you have in the stoichiometry of the reaction. So you need CO2, water, methanol, and oxygen, right? So you see here that there is a concentration number for methanol, but it's very small, right? So you see that the methanol concentration is 5.2 times 10 to the minus 17, right? So if you divide by 10 to the minus 17, you're going to have a huge equilibrium constant. So you're going to say, well, if your calculator or the spreadsheet can handle those numbers, it will give you something times 10 to the 20 or something, right? You say the equilibrium constant is still very high at 2500 K, right? The equilibrium constant is going to decrease with increasing temperature because this is an exothermic reaction. But still at 2500 K, the equilibrium constant is very high. So you cannot calculate it from the equilibrium composition. Right? But for all practical purposes, especially for engineers, that means that all the reactants have been converted to products because the equilibrium constant is so high. The conversion of methanol, if you calculate the conversion of methanol, you see it goes from 12.3% to 10 to the minus 17, right? So basically all of the methanol is converted, which means that the equilibrium constant is very high. And something to that effect has been posted on the class website as a hint regarding this calculation. So it's CO, methanol, anything else in the statement of the homework problem?
N2 plus O2.
N2, right? So that one is more interesting, right? Because that's an endothermic reaction, right? So let's do N2 and O2. So now we go back to C1 equilibrium. At 2500, the reactant species. So let's erase this.
For me, more factors we can calculate K.
So now the fuel is N2. One mole.
So I'll send it to you guys. And then you
One
can
mole of
send
N2.
it to
The oxidizer is again air, and the complete combustion products are now going to be again so what are the complete combustion products going to be here is an interesting question, right? So let's clear all here and auto-populate, right? So the complete combustion products, M2, right? So this doesn't make sense, right? So what we need to do in this case is not use the automatic fuel and oxidizer selection, but simply select as the reactant mixture N2 and O2, right? Air, right? So let's select air as our reactant. So in this case, we eliminate the equivalence ratio selection, and our reactant is simply air, right? So species N2. Species, where is our N2? N2. So that's going to be 0.79. And O2. And that's going to be 0.21. So we are entering air. So that is, those are our reactant species. So let's go to run calculation, create input file, and this one we have to view it so that we are sure that we've entered the right thing. So you see here that we have the 2500 K, 1 atmosphere pressure, and our reactants are nitrogen and oxygen. Okay? Yes?
I got some that says size.
So let's take a look at that. Well, that's some optional math selection, which is irrelevant unless you get an error. So let's close this, and let's run the model, and let's view the results. So this is an endothermic reaction, of course, for which the equilibrium constant is going to increase with the increasing temperature. There it is, right? So here you see we started with 79% nitrogen and 21% oxygen. We ended up with 19.5% oxygen and 77% nitrogen. So here, of course, and the product is NO. So what you want to calculate here is the concentration of NO divided by the concentration of nitrogen to the power of 0.5 and the concentration of oxygen to the power of 0.5. And you will get an equilibrium constant, right? Which is going to be relatively small, right? And then you change temperature. At 2000, it's going to be even smaller, right? So you can calculate the conversion of nitrogen here, right? The conversion of nitrogen is 0.79 minus 0.77 divided by 0.79, which is a relatively low conversion. Yes? I'll take a look at that.
So you gotta output that how many times for temperature? Does it take a lot?
I think I did 500. 15 times 12.